preparing for a quantum algorithms engineer interview, you've reached Candy Mentor, and this video is for you. We'll walk through 15 key questions you're likely to face. For each question, you'll see a sample answer followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. How do you decide whether a problem is a good candidate for a quantum algorithm? I start by separating quantum speedup from quantum hype. A strong candidate problem has structure that maps to amplitudes, periodicity, linear algebra, sampling, search, or Hamiltonian dynamics. I also ask whether input loading, oracle construction, and measurement cost erase the speedup. For NISQ hardware, I prefer problems with shallow circuits and tolerance for approximate answers. The practical test is end-to-end complexity, not just a faster subroutine. While answering, focus on end-to-end advantage, problem structure, oracle or data loading costs, output extraction, NISQ constraints, and how you would compare quantum complexity against strong classical baselines. Question 2. Explain the Quantum Fourier Transform and why it is central to phase estimation. The Quantum Fourier Transform changes the basis so periodic structure becomes phase information. In phase estimation, I prepare an eigenstate, apply controlled powers of a unitary, run inverse QFT, and measure an estimate of the eigenphase. This pattern powers Shor's algorithm, amplitude estimation, and chemistry algorithms. The key engineering details are controlled unitary synthesis, precision bits, and success probability. More precision means deeper circuits, so resource estimates matter. Make sure to cover basis change, phase kickback, inverse QFT, controlled powers of a unitary, precision versus circuit depth, and applications like Shor's algorithm and eigenvalue estimation. Question 3. How does Grover's algorithm work, and what makes oracle construction difficult? Grover's algorithm gives a quadratic speedup for unstructured search by amplifying marked states. I describe it as alternating an oracle that flips the phase of solutions with a diffusion operator that reflects around the mean. The hard part is rarely the diffusion step. It is building a reversible, low-depth oracle. If checking a candidate is expensive, the advantage shrinks. I would estimate query complexity, gate depth, ancilla count, and noise sensitivity before claiming usefulness. In your answer, talk about amplitude amplification, phase oracle, diffusion operator, quadratic speedup, reversible computation, ancilla management, query complexity, and why oracle cost can dominate real implementations. Question 4. Walk me through Shor's algorithm at the engineering level, not just the theory. Shor's algorithm reduces factoring to period finding. I would choose a random base, build modular exponentiation as a reversible circuit, use phase estimation to recover the period, then derive factors classically. The algorithm is asymptotically powerful, but the implementation cost is dominated by fault-tolerant modular arithmetic. On today's hardware, demonstrations factor tiny numbers only. In an interview, I would separate algorithmic complexity from physical resource requirements like logical qubits, T-gates, and error correction overhead. Be sure to mention reduction to period finding, modular exponentiation, phase estimation, continued fractions, fault-tolerant resource needs, logical qubits, T-gates, and why current demonstrations are limited. Question 5. How would you design a variational quantum eigensolver for a molecular Hamiltonian? VQE solves ground state estimation by splitting work between quantum state preparation and classical optimization. I prepare a parameterized ansatz, measure Hamiltonian expectation values term by term, and update parameters to minimize energy. Good engineering means choosing an ansatz with enough expressivity, but not too much barren plateau risk. I also group commuting polyterms, reduce shot noise, and benchmark against classical chemistry methods. The trade-off is shallow circuits versus optimizer instability. While answering, cover fermion to qubit mapping, ansatz selection, expectation measurement, classical optimization, shot noise, commuting polygrouping, barren plateaus, and benchmarking against classical chemistry methods. Question 6. How would you apply QAOA to a combinatorial optimization problem like MaxCut? QAOA frames a combinatorial problem as alternating cost and mixer evolutions. For MaxCut, I encode edges in a cost Hamiltonian, start from a uniform superposition, apply p-layers, and optimize angles classically. I would discuss how performance depends on graph structure, depth p, optimizer choice, and noise. It is attractive because circuits are structured and hardware-friendly, but classical heuristics are strong, so benchmarks must be honest and problem-specific. Make sure to explain cost Hamiltonians, mixer Hamiltonians, circuit depth p, parameter optimization, graph structure, hardware connectivity, approximation quality, and comparison with classical heuristics. Question 7. What is quantum amplitude estimation, and when is it better than classical Monte Carlo? Amplitude estimation improves Monte Carlo scaling from roughly 1 over epsilon squared to 1 over epsilon in query complexity. I describe it as estimating the amplitude of a good subspace using phase estimation like interference. In finance, that can estimate expected payoff, but only if state preparation and payoff oracles are efficient. On NISQ devices, iterative or maximum likelihood variance avoid deep QFT circuits. I always include confidence intervals and oracle costs in the claim. In your answer, discuss amplitude amplification, query complexity, confidence intervals, state preparation, payoff oracles, QFT-based and iterative variance, NISQ limitations, and financial or risk analysis use cases. Question 8. Compare different approaches to Hamiltonian simulation and when you would use each. Hamiltonian simulation asks how to implement time evolution under a target Hamiltonian. I would start with product formulas for simplicity, then compare Taylor series, LCU, qubitization, and QSP methods for better asymptotics. The choice depends on sparsity, locality, norm bounds, precision, and available fault tolerance. In chemistry, mapping fermions to qubits using Jordan-Wigner or Bravy-Kitaev is part of the pipeline. Resource estimates decide whether the algorithm is realistic. Be sure to cover Trotter-Suzuki formulas, LCU, Taylor methods, qubitization, quantum signal processing, sparsity, locality, precision scaling, and fermion to qubit mappings for chemistry. Question 9. What is the difference between quantum error mitigation and quantum error correction? Error mitigation reduces bias without fully protecting the computation. Error correction encodes logical qubits and actively corrects faults. For NISQ experiments, I might use readout mitigation, zero noise extrapolation, probabilistic error cancellation, or symmetry verification. These improve estimates but add sampling cost and assumptions. Fault tolerance is the scalable path, but it requires many physical qubits per logical qubit. I would be clear about which regime an algorithm targets. While answering, distinguish NISQ mitigation from fault tolerance, include readout correction, zero noise extrapolation, probabilistic cancellation, surface codes, logical qubits, sampling overhead, and scalability limits. Question 10. What are barren plateaus in variational quantum algorithms, and how would you mitigate them? A barren plateau is an optimization landscape where gradients vanish exponentially, making variational training ineffective. I look for causes like overly expressive random ansatzes, global cost functions, excessive depth, and noise. Mitigations include problem-inspired ansatzes, local costs, layer-wise training, parameter initialization near identity, and symmetry constraints. In practice, I monitor gradient variance and optimizer behavior early. If training needs impossible shot counts, the algorithm is not practical. Make sure to mention vanishing gradients, ansatz expressibility, circuit depth, global versus local cost functions, noise-induced plateaus, initialization strategies, layer-wise training, and diagnostic gradient statistics. Question 11. How does quantum circuit transpilation affect algorithm performance on real hardware? Compiling a quantum circuit is not just translating gates, it changes depth, error rate, and feasibility. I map logical qubits to hardware connectivity, decompose gates into the native basis, insert swaps, and optimize cancellations. For superconducting devices, 2-qubit gates usually dominate error, so routing matters a lot. I validate the transpiled circuit, not just the abstract circuit. A beautiful algorithm can fail if compilation doubles depth beyond coherence limits. In your answer, cover native gate sets, qubit connectivity, routing, swap insertion, 2-qubit gate errors, circuit depth, calibration data, scheduling, and validating the transpiled circuit. Question 12. How would you reduce measurement cost when estimating expectation values in a quantum algorithm? Measurement design controls both accuracy and runtime. If an observable is a sum of polystrings, I group commuting terms, choose measurement bases, allocate shots based on variance, and combine estimates statistically. For VQE, measurement cost can dominate circuit execution. I also watch for readout error, covariance between grouped terms, and confidence intervals. The best answer shows that sample complexity is an engineering budget, not an afterthought. Be sure to discuss poly decompositions, commuting term grouping, basis rotations, shot allocation, variance reduction, readout errors, covariance, classical shadows, and confidence interval reporting. Question 13. How do you use classical simulation when developing and validating quantum algorithms? Classical simulation is my first validation tool. State vector simulators are exact, but scale as 2 to the number of qubits, while tensor network methods exploit low entanglement or circuit structure. Stabilizer simulators handle Clifford circuits efficiently, but non-Clifford magic increases cost. I use simulators to debug small instances, compare against exact diagonalization, and estimate noise sensitivity. If a proposed quantum advantage is classically simulable, the claim needs refinement. While answering, include state vector simulation, tensor networks, stabilizer simulation, exact diagonalization, noise models, small instance validation, scaling limits, and detecting claims that remain classically simulable. Question 14. What metrics would you include in a fault-tolerant resource estimate for a quantum algorithm? Resource estimation translates an algorithm into physical feasibility. I count logical qubits, circuit depth, T-count, T-depth, magic state factory cost, and required logical error rate. Then I map those to physical qubits using an error-correcting code and assumed hardware error rates. For algorithms like phase estimation or Shor, asymptotic complexity is not enough. The interview-winning answer connects algorithm choices to concrete runtime and hardware budgets. Make sure to cover logical qubits, circuit depth, T-count, T-depth, magic state distillation, target logical error rate, physical error assumptions, code distance, and runtime estimates. Question 15. If asked to implement a new quantum algorithm prototype, what workflow would you follow? I would build the algorithm like a scientific product. First, define the target problem, success metric, and classical baseline. Next, implement a small verified simulator version, design oracles or onsetsa, and estimate resources before running hardware. Then I test noise models, transpilation results, and measurement strategy. Finally, I report uncertainty, failure modes, and scaling projections. That workflow prevents confusing a toy demonstration with a deployable quantum advantage. In your answer, talk about defining success metrics, choosing baselines, simulator first development, oracle or ansatz design, resource estimates, noise testing, hardware execution, reproducibility, and honest scaling analysis. If you are still with us, congratulations. You are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.